HTTP request smuggling was one of the most advanced attacks that I had to test for the application. So you will see that there are plenty of variation of the attack, and it has tons of important detail regarding how to exploit it, how to detect it, and just how it works. That it's pretty complex to understand. So we're going to see what are the different vector of attacks. So in the slides, I will detail plenty of attack vector and some payload variation, but we're not going to do obviously labs for 10 variation with small details on the attack. What we're going to see after some example, what are the defense and mitigation, and then some conclusion from my slide, and then we'll follow up with the labs because you're here because probably it's a workshop and you want to see in action. So this presentation, I'm trying to do an introduction. So this is not a new novel attack or variation of this technique. I wanted to do a summary of what were the key research on the topic. Because if you're looking at the different presentation, for example, at Black Hat, every year they bring some new aspect to the attack, new maybe vulnerability that they have found in actual infrastructure or a new variant. But it's really interesting to see what was the evolution of the attack. I think it helped in the understanding of this vulnerability, especially because the earlier payload were much more easier to understand. So actually, it's a vulnerability that it dates back to the 2005. It was first documented in a paper called HTTP Request Smuggling by 4 researchers at Watchfire. And then there was a big gap between that, almost 10 years or more. There were a few articles that were published, but very minor stuff. And then in 2016, new variant came up, presentation by Régis Leroy, alias Régis Leroux, that presented at DEF CON. And even this presentation, it was really under the radar, didn't get much publicity, even though we found vulnerability in very high-profile proxies. And then in 2019, James Kittle found vulnerability that he was able to demonstrate on actual infrastructure and got plenty of bounty with additional variant that he found. So, and from there, multiple research came out of this. And we're going to see some variant in this presentation. So first, to understand HTTP request smuggling, we need to understand a feature of HTTP that is called tunneling. Tunneling is a feature that was not there initially when the web was created, because early version of the web were very basic web page. So think about just HTML web page, just purely academic website or very basic text-based website. But as soon as the web become more rich, now we have images that are included in page, we have style sheet that are included in pages, and plenty of other resources. In early version until HTTP 1.0, every request needed a new TCP connection. This means that your client, the web browser, need to do a TCP handshake every time for every user. So you might say, I'm just loading one page, but this web page can load 4 JavaScript file, a CSS style sheet or more, plenty of images. So this is a lot of communication that could be unnecessary. Also, we're going to see for infrastructure that are between system communication, for between a proxy and backend or backend to backend communication, it's important to have connection pooling. So connection pool are, you maintain a number of connection between a system, and you reuse those connections. So these are called connection pool. It's used for connection with database, and it can also be done with HTTP. This became possible in HTTP 1.1, and this is where HTTP request smuggling starts. We're also going to see that transfer encoding header is something that was introduced in HTTP 1.1 that is a key feature that introduced many variants to the attack. So why HTTP tunneling or the effect of pipelining introduce request smuggling? If we have multiple clients that are connecting to a proxy, and this proxy is connecting to microservices or a backend. So we're going to see later what proxy are used for. The proxy doesn't want to create internally plenty of TCP handshake and tons of network traffic. It wants to minimize its footprint and be as efficient as possible. So he's going to maintain numerous connections. And for example, one connection could receive 2 requests from one client, and those 2 requests will be placed side by side in the same socket. And this socket will still remain open also for a second user, because we have a continuous flow of requests from different clients, and all these requests, those HTTP requests, are contiguous in the same TCP socket. So the separation between each of these requests is key. Otherwise, if we don't know where each request is ended, we will not give the response to the right request, or we will not interpret the request correctly. So how do we know where each request ended? We have, for example, here a stream of multiple requests, and here visually it looks intuitive. Like we see a kind of a pattern for HTTP requests, and I've also removed most of the header, but basically everything is based on the content length header. So every request in HTTP 1 is has a section that is our headers. So the first section, and then we have a body section that is optional or could be of length 0. So if we're just fetching a page, we just say it's going to be content length 0. However, if we're submitting value to a form, like a login, then we need to specify content length, because the body section will have it will be a variable length depending on the request. For the header section, headers are theoretically unlimited, while the RFC has some big length that is allowed. It should be almost unlimited, and it's only until there's a new line at the end of the header that is terminating each header line. So with content length, it seemed pretty obvious how can we separate each request. We just look at those, and based on this, we know where the next request will start. If, for example, we're the backend and we're receiving a continuous flow from proxies. And we're going to see proxies in practice in plenty of places. Almost all production environment for a web application will have a proxy if they have some kind of load to support. Because if you have a load, you're going to need to do load balancing to distribute the number of servers that can handle some requests. Otherwise, if your eShop is based only on one server, you're going to need to have plenty of memory, plenty of CPU, and it's going to be less effective than if you're doing this distributed environment. Also, we can add some feature like caching or firewall. So we might have different application in our backend. So maybe a blog, a website, eShop, stuff like that. And these will all be using different technology. So for this reason, sometimes it's just easier to have a proxy that will be in between and add some functionality like filtering maybe for security, potential security vulnerability that could be exploited. They might do some additional validation. If we need to cache some resource, so if I have a small Node.js application running in the backend, Node.js might be really efficient at doing async stuff. It's not super efficient to serve all your images and CSS constantly from this Node.js application. If you can have some of your static resource cache, like JavaScript file, it will be a big benefit. So that's just why do we have proxies. I wanted to make it clear because if you want to identify this vulnerability, you need to identify the scenario where it's applicable. So, and sometimes the proxies will see one request and the backend will see two requests sometimes. Or sometimes it's going to be two requests, but the two requests will be interpreted differently. And this is where request smuggling comes in. We're going to have two different parsers that are looking at byte stream and looking for HTTP messages. And the proxies will see one request, but the backend would see it a bit differently and will see actually different resource being loaded. How is it possible? It's possible because the implementation is usually based on RFC, but RFC will omit some detail regarding some malicious behavior. Like the RFC will document for the HTTP protocol what the different headers are doing, but what happens if a malicious client introduces a duplicate header in the same request? So here in our example, we have two bucks that are two byte stream that are actually identical aside from the colors. And we're going to see that the proxies interpret the same message completely differently. And this will be because the first implementation, so the proxies, will only keep the value of the last header here for content length because it's duplicate, while the web server, so our backend, looking at the same byte stream will look at only the first header. And this is problematic because the attacker did this with some intent. The content is different for each of these headers. So the proxies will see that index.htm is being loaded and test.htm. So we can see that the second request starts right after the X in red. And the backend web server sees actually that it's a REST call to maybe dynamic value that loads profile information. So here it's loading profile slash 1237.json. So this can cause problem because if you have, for example, a caching feature on your load balancer or your proxy, then the proxy thinks that he's loading test.htm for the second request. But in practice, it's a loading profile request. So then suddenly the attacker might be able to inject some malicious HTML and it will be cached under a resource name that will be public. So this is helpful for an attacker if he wants to do advanced phishing. So having a web page on the actual company that you're targeting can be better than that. So if you are able to craft a fake login page on a company web page, it will be pretty efficient for phishing. It can also be an opportunity to maybe override some JavaScript resources. So this is the caching attack vector. There are some other additional vectors. So we're going to see example of URL filtering bypass, where the host is trying to block maybe some specific path because there are some development paths that are being exposed internally, and we don't want those to be available externally. We might want to blacklist some hosts that are internal. Additional vector, we have a credential hijacking. So this will be the capability to intercept content from requests that could be credential, but actually it's any content that could be hijacked. So we're going to have a post request, and we're going to see an example where we can actually dump this request and see it from a different computer completely. We're going to have a persistent XSS. So there are kind of two scenarios for XSS. We're going to see one where one XSS might actually not be exploitable because of a specific condition, like if you have XSS in a user agent, you know that user agent can be forced on a user aside if from the backend is actually having a user agent as a get parameter. But we're going to see that we can turn impossible XSS into persistent XSS that are actually forward directly to the user that is visiting the website. This will be the first lab of this workshop. And then we have also open redirect. If we can force any response to the user, like XSS, we're also going to be able to do open redirect with header location or just plain JavaScript. So we saw a basic example that was easy to understand with content length header that were duplicate. Most of the modern technique involve using transfer encoding chunk. And what is exactly this header? Transfer encoding is used for encoding like gzip or some alternate encoding for the body section. But actually, chunk is not related to encoding in sort of character encoding. It's specifically regarding length of the body. So instead of having in advance, this post body will be of size 100, we're going to be able to send a few parts one at a time and only specify the length for each chunk over time. So this is helpful if you have, for example, you're generating for your application a large XML document that is based on reading maybe a client from a database or product, or maybe you have 10,000 product and you want to export it, but you don't know ahead what will be the exact length of this generated XML. So instead of loading everything in memory, counting number of bytes, using content length, you can use the feature of transfer encoding with chunk mode. And here we can see that the first chunk is of size 5, followed by hello, so 5 characters, and then 2 new lines, or actually it's a return and new line. So every part is always start with the length, then some new line, the data, and then some new line. How do we finish this stream? It will end as soon as we have a 0 length chunk. So this is helpful for response, but actually it can also be used for request. So the client, even though browser might not use this, maybe aside from a potential upload feature, it will rarely be used from actual client, but for our attack, it will be pretty helpful because we can do the same. So for requests, so I'm posting to maybe a login page or index.php, And the content of the post data can be in multiple parts. And the reason it can create some confusion and is that suddenly we have two ways to define the same feature. Like we can have a content editor and transfer encoding at the same time, and both are describing the length of our body section. So what does the RFC actually says? It says that the transfer encoding should always be taken in priority. If both are present, a content length should be ignored. And the thing is, in early version of HTTP1, maybe not everybody had implemented a transfer encoding. So sometimes there would be some backend that didn't support transfer encoding. So there could already be some confusion between two parsers, because what we're going to look along this presentation is some small differences between proxies and backend that will introduce some parsing difference. So in the first paper, this scenario with transfer encoding and content length was presented, but here I'm going to present some example of variant that were found later on. So Régis Leroy, at his DEFCON presentation, present one of the scenario where he found that, I think it was in Node.js, when it was parsing for header, the parser was flexible in the sense that if there was, instead of /r/n character, only the /r, Node.js would see it as a valid header separator. The problem is that it's not, proxies won't do it this way, at least most of them. So suddenly we have a mismatch between how the length of the actual request is evaluated. So here we will have cases where the proxy sees only one request, and it's going to forward it to the backend, and the backend will see actually two requests, two distinct ones. And if we look closely at the request, because for each of those payload, you really need to take your time to visualize how the proxies will potentially parse the request and how the backend will do. So in my slide, I put in bold what are the key things that each party will see. So the proxies, it will be using content length here because it doesn't see the transfer encoding header actually, because there's just a /r, so it just seems to be a header value for the dummy header. So because it's 121, it will grab all the rest of this byte stream as the post body. So here actually, instead of a get request, it should have been a post request. So this is a small mistake. But nevertheless, these should have been two post requests back to back, but our backend will, instead of seeing one, will see two requests and will ignore the content length because the RFC suggests that you should be using, but actually it's not a suggestion. You should be looking at transfer encoding in priority. For this reason, it's using chunk mode. And the first section of the post body is just len 0, then 2 new lines. So this means that this body is just closing instantly, and everything that will follow is already a new request. So with these small differences, suddenly we have a request done to update profile. And in this case, if we are sending just, instead of a complete request, just a partial one, we can inject a prefix to the following request. So because we're in a pipeline of multiple requests being placed in the same socket, This update profile could be, for example, forced to another user with this payload, and suddenly the get slash whatever page will be ignored, but the session cookie will be attached because everything is being concatenated, and then suddenly we have a request that is forced to the user. This is called connection hijacking or content hijacking. What are some of the other variants that were found? So this was some of those were found by James Kittle. So many implementation for backend, when they just saw transfer encoding, didn't look at if it was chunk or not. So, or by default, they would fall back to chunk if it's not something that they recognize. Sometimes some supported new line or tabs between values and header name. So these are just some examples. Sometimes just instead of doing exact match, they will look at does it contains chunk in our values. So all those small differences, if you look at the code of proxies or HTTP stack from a web framework, you might be able to looking at the code to see some behavior that is, I would say, more naive, or sometimes it's just to help the developers. So it's often with good intention that it was implemented. So they might have say, okay, we're going to have people that are coding their HTTP requests with sockets and just for testing, and they might not have some /r/n, they are just using /n. Big deal, we're going to accept it. But here it can cause problem with request smuggling. Just some terminology. So transfer encoding was mentioned in the first white paper, and plenty of variations were introduced by Régis Leroy in 2016. And you will see in documentation, if you look at the research, often those acronyms. So CL.TE means content length and transfer encoding. So the first part is always what the front-end proxy, or actually it's just proxies, but if you look at James Kittle research, he's often calling proxies as front-end, but I think it's more correct to use proxies. But basically, first part is what the proxy will evaluate, and the second part is what does the backend see. And maybe another example here, again with similar technique, but just to show you what are the effects of it. Here it's going to be how can we hijack some credential using no, actually, this is an attack that James Kittle used to first leak some private headers that were sent between proxies and backend web server. First, he identified that there was a field that was reflected, and this field was login email. And this is key if you are finding a pattern for request smuggling, and you want to have to leak some requests from either that one that you have created to leak some headers, or just plainly access credential that would be posted to the web service. You need to identify fields that are reflected in the page. The fact that the value is escaped or not will not be important here. What is important here is that we'll use an incomplete request as a prefix to grab content from the following request, and then it will be reflected to us. So how James did it, he used two transfer encoding header. The first one being chunk and the second one X. So it's only the proxies that will keep the last header. And just like the content length example, here, because we're overriding the value based on the last header that we saw, actually transfer encoding will be ignored. So here, content length will be used because transfer encoding is just seen as invalid. And for this reason, all the left section will be seen as one request by the proxies. But for the backend, when it will receive it, because its implementation is keeping only the first value, and when it sees duplicate header, it just skip them. Then suddenly we have a second request that start, and here we have the control over pretty much all the header. And for this reason, we're going to see the content length is longer than the data we provide. The only data that is required is here we're forging a post parameter login email so that when we'll get the response, because we can send those, but maybe in another request, basically somebody will get is this value reflected. So if it's we want to leak some data here, actually the next request will be the attacker. So there will be a third request that could be anything. And here we have for the login request, sorry, not being too clear, but the second request is going to do a post to the login, and a response is going to be prepared that is reflecting the complete content of the next request. So if we send another request, we're going to get the response from this this pending request, basically, because the proxies already responds to what he thought was only one request, but the backend is responding to a request that is not completed yet. So the next user will receive the response for this login post. What he ended up what he found with this pattern on this endpoint is was able to found a header that were reflected that includes some authentication token, and he was able to then forge a request to internal services, I think. But the first part was leaking headers. Another example here with similar pattern, but here we're prefixing an XSS pattern that will be forced to a user. So it's going to be similar. I'm just going to look at the second, the right part. So we're doing a post to index.php, and here it's inspired from an example given by also James Gettle. The SAML post parameter, I mean, is a reflected XSS, but in some cases, it will be much more hard to ask a user to visit a link to then be a CSRF being done, and then the XSS happen. Sometimes you have a CSRF token, so there can be plenty of protection that will make this not work, even though this SAML field is reflected on escape. But here we're pushing from basically it's from the keyword post to the third one post. We're pushing a prefix, and the next user will be the victim. His request will be happen to this one, but in practice it will visit index.php no matter what page it's visiting. So it could be visiting contact page. In practice, the resulting page will be index.php with the SAML parameter, along with some junk that will be basically the request of the user. But it will be effective to do an XSS that will be forced to the next user. So if you're doing this attack in production, you need to be aware that this has high risk of just desynchronizing HTTP tunnel, so it can break the session of plenty of users. So if you're creating a desync, you're not targeting a specific user. Basically, the next one is going to be the winner to have some breakage. So the effect will depend. So if it was loading the user JavaScript file, this could have an effect, like you have a successful XSS potentially. But again, forging a valid JS file will be hard, but in practice, it might just break the page it's visiting, break resources that it's loading, like images or stuff like that. It can break plenty of things. And once the desync is done, it can be there for a long time, so it can cause some temporary downtime for a couple of users, at least for a moment. So this is just showing that we will be sending our stream that will be interpreted as two requests, but the response to will be seen by another user. The demo, I'll be doing it in the lab, so it will be this exact attack that we'll be demonstrating. So this means that we're close to the end of the theory section. So for mitigation, actually, most of the modern proxy or load balancer have received patches. This is research that was published in 2019, so it's less likely to be found, but this never means that it's going to be away, because also there are some new variants that can be found. Yeah, so, and the proxy might be totally legit, but sometimes you'll be using for a small microservices, maybe a weird framework that is implementing an HTTP parser that is more flexible. So you might be able to find some variation of what I've presented today. So the real solution is never to modify your application to somehow mitigate the fact that HTTP request smuggling can inject arbitrary requests. It's pretty much out of control for the application. Doing the update is the main solution. Be aware that, for example, when I looked at the mitigation for F5 big IP, the mitigation is to enable some rules. So many vectors are sometimes not included in the patch. Sometimes they will need some manual configuration. And big IP had two mitigation, and one of those was to enable a module that was not there by default. So re-advisory in detail, sometimes it's not a fix that will be out of the box, because they want to limit the potential side effect of existing application. But so this is not an easy problem to fix. Cloudflare, Fastly, Akamai, according to James Kettle and most researchers, the patch that were done in 2019 fixed all the issue found with alternate encoding of the transfer encoding header. And I'm not exactly sure of how they have done it, but based on what we can read on their blog, there seems to be doing normalization of requests. So while they will not give the exact code of what they are doing, when they see some potential ambiguity, they will try to simplify the request to send a request that is as what they see it. So if they see two content length, if they think that we should keep the first one, they will just truncate and remove the second header. So for this reason, they are simplifying the request to avoid confusion with the backend application. And I think it's a good design to mitigate this issue. If you want to test this issue on your backend or on your infrastructure, there are two tools you could be using. So one of those is was done by James Kittle. It's a Burp plugin, and this is the configuration section. So showing that there are plenty of variation for request smuggling, and I didn't want to present them all in this presentation because it's kind of useless. It's just small detail, but with the same principle. The other tool that was released, Régis Leroy, when he presented at DEF CON, released a tool that I didn't use personally, but it's called HTTP Wookie. It's actually a backend application that you deploy behind your proxies, and you will have a test client that will connect through the proxies to your backend, and based on what are being seen from both sides, he's making some assumption regarding if it was properly parsed or not. When I've done some research, so yeah, the so sample website.gosecure is actually the first exercise of the lab. If you are doing some tests with the Burp plugin, it seems to be doing detection based on time-based test, and it has some limited accuracy because personally I've created some web application that I could exploit for request smuggling, and it still didn't detect it with the Burp plugin request smuggler, even though I checked all the bugs and ran it. But it can still be helpful, the plugin, if you run it on a test server and you look at with the plugin flow. This is basically just a plugin that shows you all the requests that are emitted by plugins. And from this, you can search for specific pattern. And one of those is looking for 405 requests response. 405 means invalid method. And one of the key technique for detection that was even present in the first paper is just sending one character that will be prefixed to the next request. And if you do enough requests, at some point, this additional character that you've posed will be prefixed to one of your requests. And so, for example, if I'm sending one character that is longer than what the backend will see, then at some point it will create the method xget or xpose on your request, and with this you will receive 405 not allowed. So when you look at the flow plugin, it doesn't mean that the payload on the left cause the response on the right. It might actually be more the previous request or one of the previous requests that trigger this additional character, and then it got injected in the request that you're currently sending. So that's something to be aware. This behavior when you're finding it, because initially when I've got familiar more with the vulnerability, I did most of my testing with the Web Academy initially before creating my own small application with actual proxies. And on Web Academy, if you're doing exercise, one thing that maybe is missing from a real environment is that the all load balancer will have connection pool between proxies and backend. So you'll have 10 to 20 connection. This means that you'll need to always do multiple requests to confirm some tests, because requests are not contiguous automatically. You need to basically have requests in every connection to be able to test. So one thing to be always keep in mind for the labs, disable content length for the first exercise or the update content length, because this will apply to Burp, but others, other proxy, they will generate for you the content length on the fly, just to make sure that the request is valid. So, and for this purpose, but here in our case, we want to have ambiguous header. So if it's intended, just uncheck it. But after that, make sure you enable it. So I'm going to jump to the conclusion. So conclusion is just quickly a reminder that it can have multiple effects: request smuggling, cache poisoning, credential hijacking, URL filtering bypass, WAF bypass, persistent accesses, etc. Your production environment needs to be tested, but be aware that there are some huge side effects that can be occur with this. So if you just run for the first time Burp request smuggler, personally, I wouldn't do it on a client environment, just because it has a lot of potential of side effect, and you might cause the side effect and not even detect that it's vulnerable. So that's even possible. So that's only negative in this case. So look for automated tool, because there are a lot of variants to cover. So make sure your scanner is including some of these check. And some other thing I wanted to cover that is going to be in the second part is some variants. So initially, there was some payload for content length, and actually in the first paper they were mentioning transfer encoding confusion with content length, but then there was the double transfer encoding header technique in 2016 that was introduced, and additional variant in 2016, and then right after the James Kittle publication, people have found a variation that use WebSocket in HTTP2 to do the same effect as filter for that would cause filter bypass, but you're going to see that it's a more limited vector, in the sense that you will not be able to do persistent accesses with it, or content hijacking, but it's actually one of the vectors that is the most prevalent, because especially the HTTP2 vector is still working on a latest version of Nginx, Duster, and HTTP traffic server. So we'll see it in the exercise. So that's when I'm jumping to the workshop. So I'll be pasting in the chat, if I can, the link to the workshop. Okay, I'm not sure if I can, so I'll keep it in the window mode. Sorry about that. Yeah, when I'm sharing my screen, I don't see the chat, so sorry, I'm not familiar with Zoom, but basically, this is where you'll see different exercise. So the workshop is kind of a continuation of this introduction. So we're not going to do exercise for all the small variant, but we'll see one for the classic, and then 2 exercises for HTTP2. So for this workshop, just quick instruction, you're going to need to clone this repo to run it. So this is not something that I'm hosting and that I'm sharing to everybody, because we're talking about HTTP tunneling that is being hijacked. It would be a nightmare to test if everybody was using the same instance. So for this reason, it's easier for me to just give you all the source with Docker images. So this, we already saw it. This is just written differently, but we all saw this. This is just Request Smuggling 101 that we just saw. Now, HTTP Request Smuggling evolution, this is something I think can be helpful, is the evolution of the vulnerability as I see it. So kind of one of the precursor of this research was a paper on response splitting that is not the same vulnerability, but closely related to it. Then the different paper that really brought advancement to the vulnerability. So while people will see the same variant in different bug bounty or different website, is less interesting for this when seeing just the evolution. So the recent development are the HTTP2 cleartext upgrade that currently works on plenty of proxy. We're going to see how we can bypass WAF. So mod security, Naxi are kind of, it's, I don't know how much is known, but in the paper from James Miller, or the article, he mentioned clearly that it can be used for WAF bypass. And at the moment, there are no mitigation for it. We're going to see it in a lab. And this is something more recent. I actually tried to do an exercise for the latest research from James Kittle from this year at Black Hat. Unfortunately, I'm not done yet, so it almost made the workshop. But at some point, I will publish differently this workshop with this additional exercise that I find really interesting. So this is a vector of attack that involve injecting HTTP2 headers that will include new lines in the header value or header name. And because proxies are converting HTTP2 to HTTP1, it will create some injection in the HTTP message that will lead to the same behavior that we saw earlier in HTTP1 message. So if you are curious on the topic, I really encourage you to look at the different paper. There are some, it's important to start from the start to see what was found, what were the key tests they have done. Because sometimes, even though it was fixed in one software, new software came every day. So the same mistake can be repeated. This is something we also saw the pattern for duplicate content length. Then we saw what happened when we have content length and transfer encoding chunk. So what can be an issue? And this brings us to doing it in action. So once you have cloned this repo, so it will be on the first slide, you will need to run the application. Actually, that I just saw there's a small mistake. So this is the right configuration in your host file. This one is not valid. So yeah, you will have, so I will actually start the exercise, the infrastructure. So just give me a second to just find it. So the only requirement is having a burp proxy, or actually any proxy for the first exercise. You will see some different folder for different exercise. So for the exercise that was named lab 1. So in lab 1, there will be one exercise, one scenario of attack. In what was named lab 4, we will see two scenarios. The Websocket, I'm not going to present it today. It's too similar to HTTP2, and it's much less realistic, I think. And there are, we'll see it in a moment. But yeah, so every time you want to start a a lab, so lab 104, you just go to the folder, and this will work on Windows or Linux. You just do Docker Compose up. It will build potentially or fetch some images depending because every infrastructure is multiple container, so there will be proxies, backend application. So this will run as soon as started. Should be able to load it at some point. Okay, I think I've cleared my cache for Docker at some point, so it will need to re-download a couple of images. But in the end, there's no build instruction that you need to run to build the application. Everything is pre-built, and you just need to run it. So for the first exercise, we're going to do it first. We're going to detect the request smuggling. Then we're going to see that we have a potential for to send arbitrary XSS to users that are visiting the website. And yeah, and I'll demo this as soon as my infrastructure has started, so it should be a moment. Oh, I'm seeing there is. Okay. Okay, now I have the access finally to the chat. So, so there are 30 minutes left. You'll see that the exercises are pretty easy because this is not a CTF. I'm just giving the instruction. So the idea is to do it yourself, and it's much easier. Not easier, but it's better for understanding than just listening to slides. So once you have done it yourself, you can do some small tests to confirm your understanding about it. Actually, I think I'll start with. Now we still have some time, so we still have 20 minutes. So I think I'll do both demonstration. It will take probably 20 minutes back to back for all demonstration, and then you'll have the time that is remaining to do it by yourself. Yeah, so actually, if you're starting from nothing, it will take some time, as you can see, because in the case of, I think I'm recompiling Nginx, I think, but will be in a moment. Okay, no, this is a traffic server. So for the first infrastructure, it's using an old version of traffic server, Apache traffic server. So this will not work on the latest version. And if you have questions, don't hesitate to ask them in the chat. I can answer them while it's compiling. And I think I'll just finish the content for the instruction, and then I'll do the demo when it's going to be ready. So, but you can do the same thing at the same time. Just clone the repo, do Docker Compose up on the first infrastructure. If you have Docker installed, it should work right away. Some of the variants that were introduced more recently, and by recently I mean in the past year and a half, there is this WebSocket request smuggling attack that was introduced, and it has two two methods depending on what will be the proxy. WebSocket, the way it works is you will send a HTTP1 request with the upgrade header. And what does this do is that instead of following the regular HTTP1 protocol, once the server has accepted the upgrade, the following content will be pretty much identical to just regular TCP socket, where you can exchange right away chunks of byte between client and server. The main focus with WebSocket, it was to have granular control over with JavaScript. So this way, it's kind of Ajax, but more lightweight and more performant. So you have less exchange to do every time you want to have a small update directly from the server. So the way it works is first there is this kind of handshake where it's sending a request with the upgrade WebSocket header. There's also the WebSocket version header that is important. And it will be sent to the server, and then the backend that is supporting WebSocket needs to reply 101. This means, okay, I'm accepting this handshake. We're now switching to WebSocket. And then there is this communication. Some proxies, including an older version of Varnish, just didn't look at the status code that was replied by the server. If they saw upgrade WebSocket, they would assume that this client was successfully communicating with the server as a WebSocket communication. So this is the first issue. And this means that a client could be malicious and fake an upgrade to WebSocket, received 200 OK from the server that would just ignore the upgrade header, and then the client would send arbitrary requests that would be interpreted by the proxy as just an open WebSocket communication. This is the first kind of vector. The thing is now modern proxy, like if you're using a proxy pass with Nginx, they will do validation about the status code, but that's about it. They will not look at if the key is valid or whatever. So everything is based on the status code. So an additional vector that the researcher nicknamed Angel, or his real name is Michael Egorov. So an additional vector he thought about that I think is a bit far-fetched, but still possible, is that if you have an endpoint that you can control the return status code because it's doing, and that's the scenario that he's presenting, it's doing a SSRF, and the request that it's fetching, it's using the status code response from this remote endpoint and placing it in the response from the server. So now you're able to kind of fake a valid WebSocket handshake. And with this, this will work on Nginx and latest version of Varnish. But I think it's kind of limited and not much, there will be not too many proxy that, or actually server application that will have this dynamic status code. Nevertheless, this research inspired another researcher called James Miller or Jake Miller, and looking at the upgrade feature from WebSocket, he thought about using the upgrade feature for another protocol that is called HTTP2 cleartext. So HTTP2 cleartext is initiating an HTTP2 connection from an HTTP1 connection. So first, there is this regular HTTP1 send that could be over TLS or HTTP in clear. And then the server will accept the upgrade if it supports the protocol by returning 101. And here, we just need that the server support this feature. So this is the backend application. So this needs to be either your Java application, your Node.js application, or Go application. If it accepts this upgrade, now you can communicate with the backend directly. And most proxies will not see properly, will not interpret properly those requests. So they will forward the request, so the complete stream to the backend, but many WAF, if not all WAF, at the moment do not look at HTTP2 in clear text mode. So you'll be able to bypass NACC, mod security, but it's still not all server that will have this feature enabled. It's something that can be enabled for many reasons, but it's not enabled 100% of the time. Still need to be tested, and especially if you're looking for a bypass to exploit a vulnerable application, but that has a WAF in front of it, it could be helpful. So for this lab, we're going to reuse the same application that has multiple features for different purposes. And for this exercise, I think I'm going to start with demo. Oh, look at what happened. Okay, I just need to close. Okay, so before I start with the HTTP2 demo, I'm going to do it I'm going to do the first exercise and then the second one, because I've just finished downloading everything. Load. The thing also, it's using command import. So if you start the Docker instance and it's telling you, like I've just added, just show you the error. Oops. If you are seeing by an error, this just means that you have another application that is using the same port. So be careful. But if you're running one instance at the same one at the time, you shouldn't have issues. So I'm just gonna switch browser here. Up. Okay, so the first step is just to intercept the request here. So we're going to detect first that it's vulnerable to request smuggling. So that will be pretty simple. So usually we will detect it with automated script, because it can be do it manually will take some time. Let me just grab the payload that I need. So the first step is, let's say we have identify a pattern with potentially those header. Here we're going to abuse the confusion where the proxies will use the content length that is much bigger than the transfer encoding. So the backend will see this as a request and this as the beginning of another request, because it's using chunk mode in priority. Apache traffic server used to look at content length first. So if we send this, nothing happened. And this is something that sometimes in academic test environment, you will have the exploit already working at the second request. But in practice, here we're going to see that I'm going to need probably at least 10 requests, unless, yeah. So now I have this issue. I'm just going to zoom a bit. And I know time is running out, but I'll be done with the demo pretty soon. Okay. So as you can see, method now, this means that while sending this request, it was prefixed by the letter G, or it can be any character that we use for test. And for this reason, gget is not allowed. It's a bit mysterious because it's not saying the method gget is invalid, but we know because this is what we intended to create an invalid method. And now that we see the 505, this means that there is request smuggling potential. Oops, I'm going to unzoom. Now, one vector that we can find is that here in this form, if I'm adding content to this to the URL, it's actually reflected as is in the page. If we would try to create an XSS, it will not be possible because browser, even though if I'm sending you a link to it, your browser will automatically encode most character. As you can see, even though I'm sending double quote, my browser is sending percentage percent 22. So for this reason, it looks like it's not going to be exploitable. However, if we continue to do some tests, it's still not possible to exploit. But if I'm sending a character that would not be able to be sent over a browser, then we can see that it's actually reflected as is without escaping. So this means that if I'm creating this pattern, this should be a valid XSS. So I could evaluate it with burp with this and open it in my browser. It will create a prompt. But I will right away jump to attempt to XSS another user. So to do this, instead of just prefixing one letter, I'm going to prefix a complete request that includes one moment. Okay, perfect. So I'm going to prefix all this. On purpose, I put the content length I so that it could be enough for my payload. So after the foo header, the request from another user will be happened. So our second request will start here when the backend use chunk mode, while if we look at the complete length, actually it's 107. So just in case you didn't see it, I looked when I'm selecting here, I can see the length 107. So I've updated the containment to make sure everything was sent as one request according to the proxy, so Apache traffic server. So if I send this, I'm not seeing something right away because what I'm seeing the result for is just the get request, so this request. But if I'm refreshing the web page, so and I could clear my my cookie just to show that it's not yeah, there's already no cookie. So the XSS is on contact page, but I'm just going to refresh the index page. And at some point here, we can see that I think the smuggling happened. Maybe I did just one small mistake. Okay, I think I had a percentage that was there that was unnecessary. So now we have a user that is just visiting the website. And at some point, I think I have a small issue with my script. I will try the payload that I already had prepared. So this should work. It's exactly 79 character. So I've just sent it. So Apache Traffic Server put it in one of its probably 10 connections. So that's why I need to refresh multiple times before I see the result. Now it doesn't seem to right away. Let's see if it does a difference. Okay. I think I know. I didn't. No. Okay. It's already configured. Just in case. Okay. I've sent it 2 times. And now I will refresh and it works. Okay, one of the potential reason, and I kind of stage a bit the application in a sense, is that if so here we can see first that I'm loading the home page, but the response that I received is the contact page with the XSS. So that's a clear sign that request smuggling clearly worked. But one thing to be aware is that your potential victim could be visiting and loading plenty of resources. So if the contact page is returned for loading an image, it will just break an image and nothing will load. So this is one of the reasons it could potentially fail. And maybe one of the reasons it failed in my previous test, I'm using an XSS that is just doing loading an image that doesn't exist, but maybe the client at some point fetched this, or I had one JavaScript that was being reloaded. Because looking at the source, I think I only have a style sheet that was loading. So I think that would explain why the team failed, but it was still loading the home page. So for this reason, to make this attack successful, you're going to need to do plenty of attempts. First, because of the number of connection pool, just to confirm that it's working. And then to have a victim, you can need to spray. So in production, this will break plenty of things. So be cautious. That's what I would say. And now we have 5 minutes. So I'll just do quickly the demo for the last exercise, which is much more reliable, I would say. So that's a good news. Okay, I'll put it full screen. And I'll start the right infrastructure. So that people can see. So starting the HTTP2 clear text infrastructure is just Docker Compose up, and you'll be able to do the last two scenario or two exercise. And that's it. Everything is loaded. I'm just going to load it to make sure everything is working. So we have this fantastic website. By the way, if you're accessing it over HTTP, Nginx will tell you a very friendly way, hey, you should be using HTTPS. This is not an HTTP port, so that's nice. Once you're connected, you're going to see, this is just a basic website that I've done that is listing movies, and it has a detail page that receive one ID. And there is this filter on the home page where you can see genre is used as input, and it's a string. So basically, this is just a test bed I've created to do SQL injection test. And here, for example, there is this web application, but just behind it, or no, in front of it, there is this Nexi proxy on Nginx. So it's a web application firewall. Theoretically, to use Nexi, you will need to do some training, and basically by default, it blocks everything, plenty of character, and you need to kind of whitelist parameter. But here, to do a proof of concept, I'm just going to show you that Nexi is enabled without any whitelisting so far on the key parameter. So ID, if I add a single code, this is my custom error page. But we can see that the WAF is actively blocking here. But okay, I'm gonna need a second console here. And this is going to be, sorry, at the last minute. So using the command line tool is pretty easy. You'll always need to specify those to an arbitrary URL, and then there's going to be a second request. This is where the HTTP2 tunnel is open. Oops. So the second request will be in this section here when the HTTP2 request is done. You need to specify internal port, but sometimes, like in my case, it's a Golang application behind the scene that just ignore the host. So it could be localhost here, but I think everything will work. So the first thing you can do is just -t. It will do some tests and tell you if it's successful according to a test. So if it's able to open HTTP2 and the upgrade respond with the 101 status code. So now that it worked, now we can do more tests. And we're still connecting to the same service. It's just that here the tool is kind of primitive, but you can modify this proof concept code to do actual exploit. And here I'm going to show you that I can now place single quote. So here, this would have been blocked initially if I would have used directly. We just saw it on in Firefox. Oops, not this one. Neither this one. It's here. So Nexi is blocking as soon as you put single quote, but here we can see that it's not being blocked. So you'll be able to do injection. So this would have been blocked. So here there are no movie return because it's just an invalid query. And okay, you need to put the URL between double quote, I think, and you might need some encoding. Not yet. It's not the right endpoint. And then we can see that single quote actually passed. So I can. And we have an injection where the condition is working, and if we do a condition that is false, suddenly there is no movie return. So if you want to do more on this, you can actually exploit the X3 injection to access the user table, for example. But that's it for now. The exercise will be up as long as GitHub still exists. So the exercise will be available publicly. And you'll be able to do, for the last application, both the WAF bypass. So in this case, it's Nexi, but it could have been mod security. Just that mod security it's more loose than Nexi and its default mode. So that's why I found it a more convincing demo. Then you can also access an page that would be, for example, sometimes you have debug pages or monitoring pages that sometimes have RC vulnerability. So these would be blocked by default by load balancer if they have security rule. But you could access those pages if you know that they exist, or brute force them using this. So, and with this, as a conclusion, so this was a workshop of 3 exercises. You'll be able to do it by yourself. Sorry about the miss. I missed a bit the time mark. But if you are also interested in this type of workshop, we've done 3 different workshops that are similar to this format. So there is an extensive. Oops. Sorry, the sharing thing is blocking me, but you'll have similar workshop on XXC, specifically on XXC, same thing on template injection, different language, different exercise. So it's much more easier than request smuggling, but still plenty of small detail regarding exploitation that can be helpful for improving your skills. So if you have questions, you can contact me on Twitter. My contact information are actually on the slides. I will add it to this deck of, but I'll put it in the chat. Let's do this. So if you have questions, because most people I guess didn't start or didn't finish the exercise, so you can contact me on Twitter at Xstream. That's H3Xstream. So thanks for attending the workshop. I hope you've learned or about request smuggling or learn new trick about it, and enjoy the rest of Intent conferences. Are there any questions regarding the exercise or maybe something that I've presented earlier. And for those still in the room, I'll be publishing this workshop publicly probably in the next week or two. I'm just going to wait. I was going to have a fourth exercise that involved HTTP2 injection header. The thing is, it's pretty complex to put in place. It's a very specific version of Zool that I'm trying to deploy, and I'm almost there. Once it's going to be complete, I'm going to make it public, but in the sense that I'm going to publish it on social media, but it's still going to be accessible before this.